Welcome back, folks. Please take a seat. We're about to start the future survey session. Julienne Guy is going to kick us off by talking about DESI, which may or may not be a future survey.
Yeah. So I'm Julien. I work up the hill. I'm a co-project scientist on DESI, and so I'm gonna. So I have only 20 minutes. I cannot give a huge review. We also had a talk from Mike Wilson yesterday, so I tried to add the information that he didn't give yesterday. So I think it's important we just reminder of the science case, just to remind everybody that it's a fantastic project. Right? And then I talk about the instrument. I mean, we haven't had any talk about that, but I think it's important for you guys to understand that the data you have, where they're coming from. A word about commissioning, which is actually what we're doing now. And one slide about instrumental systematics. So we had a discussion yesterday afternoon about all of that, but I want to add more stuff to this. So you know, DESI is going to do a massive spectroscopic redshift survey, 30 million galaxies and quasars across all redshifts. So we had that presented yesterday. I want to remind what are the key scientific goals. So one of the primary goals of DESI is to measure expansion up to redshift of about 3.5. This is the dark measurement of the dark energy. So this is basically a data set that we had a few years ago. It doesn't include the most recent data we would get from eBOS. Here we have some eBOS from first data release, but we have now much better data that are coming. The actual measurement of the acceleration of expansion, I think, is still kind of driven by supernovae today. In fact, if you look at how W is measured, it's still today there's a high weight of supernovae, and we have few data at a higher redshift. And really, DESI will change that picture a lot by looking at so LRGs up to redshift of 1, identifying them with this essentially this Balmer break here and all those features that we see in the spectrum, like was done by BOS. ELG is at a higher redshift, where it will be impossible basically to get redshift from the LRGs because they are too faint. We will see those emission lines sticking out of the noise really at just a few sigma. I will show you later how a little bit crazy it is to try to measure the redshift of those galaxies at high redshift. And especially we are betting a lot on the O2 doublet, where we will have the resolution. We have the resolution to measure this O2 doublet, and so that will be important to identify those galaxies, and that's basically what's giving us the redshift range here. 1.6 is when basically you don't see any more O2 with the CCDs. Higher redshift. ELGs will be it's going to be difficult to measure distances precisely with ELGs at about a redshift of 1.5. And that's where I think the quasar sample is going to play a very important role. But also, as we discussed, with quasars comes new challenges. They are very variable objects. There's no quasar, I mean, quasars are a different one from the other. We will have larger uncertainties and redshift. So for ISD, it's going to be complicated. It's very degenerate. But also accuracy of redshift in eBOS was rediscovered the fact that the redshift of a quasar is actually kind of difficult to define because there's a lot of moving pieces in active galactic nuclei. And at higher Z, we have the Lyman alpha forest, for which I think it has been demonstrated with BOS and eBOS that we can do a really good job. And this is guaranteed science. So that's one of the key goals of DESI, but and just insisting on that, this is a projection that we have. This is done mostly by Pat McDonald and others. On the precision we will get on W. So only using BAO, we will have a precision of 0.22. So that's 2 times better than what we have today. So it's very significant. And it's also, I think, important, especially for this audience, to see how much you gain when you're starting to really understand the power spectrum to high K. I mean, we will be able to gain a factor of 2 here. So just in terms of dark energy, all the work that is being presented during this workshop will be immense for the measurement of dark energy. But of course, we have also this promise of an amazing measurement of growth rate. If we can do it, that will be totally a game changer, I think. Also, constraints on primordial power spectrum better than Planck. And what I find very exciting is that, again, if we understand the power spectra to high K, constraints on the sum of neutrino masses of 0.02 EV, so we will measure the neutrino masses. It would be incredible, I think, that we can actually, even if in normal hierarchy, minimal mass, we are going to measure the neutrino masses if we do a good job analyzing this data. So it's a great project, I think, for this coming decade. So now the instrument, an overview. So it's happening in the dome of that telescope, which is from the late 60s. So top of a Kitt Peak, that's 1 hour from Tucson here. What we did, because in fact the instrument is ready now, we replaced the top end. We had a new prime focus instrument with a new corrector, 5,000 fibers with robotic positioning, and an 8 square degree field of view. Very long fiber cables of about 50 meters, and then 10 spectrographs to analyze all of those spectra from the 5,000 fibers. So I'm just showing pictures just to tell you that what happened over the last 2 years. So starting in February 2018, people started to dismount some elements of the telescope. This was an impressive moment where the whole top end of the telescope was removed. Here, this is more than 4 meter diameter here, so it's pretty big stuff. April 2018, when the cage and the ring were delivered at the Mayo, the full corrector arriving at the Mayo in August 2018. So you see the size of the corrector. I'm going to show more slides here, and you see also this hexapod that we have here to adjust the position of the corrector. So this corrector is composed of 6 lenses. So the biggest one is 1.1 meter. In the middle here, you have 2 of the lenses are actual prisms that corrects for the atmospheric refraction, which is very important for fiber spectroscopy. And the most important new thing that came with DESI is this focal plane with 5,000 robots. So this is one of those robots. You have 2 little motors that move around the fiber. So it's distributed in petals. You have 10 petals. With those fibers come extra equipment. So first, what we call fiducials, basically dots of light that we can turn on and off that gives us the geometry of the focal plane. And guide focus arrays, which are CCDs all around the focal plane for guiding and also for the autofocus of the telescope. Another picture of that, just to show you how complex this instrument is with the electronics behind. This is the hexapod, and this is a focal plane fully installed in August of 2019. So last summer, we had all of that installed. On the other side of the fiber cable, we are presenting all of the, so we have 10 spectrographs, and for each spectrograph, we have a slit head with 500 fibers here on a curved line, which is actually the the focal surface of the spectrograph. Each fiber has a diameter of 100 micron. And each spectrograph is composed of 3 arms going from UV, so 350 nanometers to about 1 micron, basically everything you can collect from the ground with CCDs. So with dichroics and 3 different arms. This is an image of all those 10 spectrographs in the Coude room, which is one of the rooms just below the telescope. It's a thermally controlled room, so we really control the temperature at 0.1 degrees C, and it's very important to get an excellent stability of the optics. So all of that is ready now. So we have all of our equipment in place. We had our first slide on last October 22nd. Basically, it was really the first day. You have some spectrograph, you point to zenith, and you integrate for a few minutes, and then you get immediately data. And then we pointed to that galaxy and got a very nice spectra of some region of the galaxy where you see the O2 doublet and some other lines. At that time, we had only 6 spectrographs ready, and only 1 was connected to the focal plane. And we were very happy. I mean, I'm just saying that for people that are working on those kind of projects, you work for like 6-7 years before this kind of first slide. So if you're working on instruments, it happens once every decade that you have this kind of first slide. And now we're a little bit less happy because we are in commissioning now. And so we are facing all the troubles of the instrument. So it's a difficult time, but at the same time, very exciting. So basically what we mean by commissioning is testing, validating, and calibrating all of the components of the instrument and all of the software. And it's complicated, and so we had a lot of trouble. But we are making progress. I think we have a very good pointing of the telescope. The guiding is almost okay. The focus, the autofocus still has to be actually applied in real, but it was working pretty well. Spectroscopy on blank sky, I mean, without even moving the positioners, you have blank sky and you can do a lot about understanding the stability of your instrument, how well you can subtract the sky. I'm gonna come back to that. This is working well. And now we are a little bit stuck. I mean, we're making slow progress on the fiber positioning loop. Basically, all of this software that allows us to get the fibers exactly on the galaxies, we have to have them at a precision of 0.1 arc second if we don't want to lose a light. And we are not there yet. So we are working on that. And just to give you an idea, basically, you have some stars that you see in your guide focus arrays here. Here you have about 1.2 degrees from the center of the field of view, and you're trying to understand how a galaxy is going to be in, for instance, that part of the focal plane, and to move your positioner very accurately here. So it's some work going on today. So, but just a few words about the spectroscopy. I mean, you're working on spectroscopic survey, so you've been talking only about sky coordinates and redshift. I mean, before that, I mean, there are actual spectra of galaxies. And those spectra of galaxies are actually just electrons trapped in a CCD at some moment, okay, that you are moving around. So this is one of those CCD images, actually not from last night, but from the night before, because I had to do my slide at some moment. It's one of the 30 CCD images we have for each exposure. So each vertical line here is a spectral trace from one fiber, and those curved lines here are the sky lines. So here you have fiber number, basically 500 lines, and here wavelengths. All those things here are cosmic rays. So I'm zooming in here and here. And for instance, we have lights from bright stars today in our images, and you see how how separated the different spectral traces are. It's super important. Otherwise, you immediately get crosstalks between the different spectra, and it's a mess. For instance, for Lyman alpha analysis, if you start to have crosstalk. And you see also a little bit about the resolution here, which is fantastic for this instrument. So our preliminary studies show that we are able to model the sky and subtract the sky pretty well, because when we subtract the sky, we are almost at the Poisson noise level. And so from our simulations, that tells us that we will be able to measure the redshift of emission line galaxies, but we still have to demonstrate it with real emission line galaxies. This will happen in like a month from now. So, and just to maybe to finish up and give you some ideas of the challenges we have. Okay, so I've been a bit fast. Some of the challenges we have ahead of us, I'm showing again some simulation that I presented in some reviews a while ago. So this time it's a simulated image. In fact, it looks a lot like what you just seen, which was real data, but this is here a simulation. In that simulation, for instance, I'm going to look at one of those fibers where we have an ELG at a magnitude of 23, a flux, O2 flux, that is this value, which is what we think we will be able to detect at a redshift of 1.3. So you have this ELG here, and then you have another fiber next to it. And I don't know what you did. I think it's a sky fiber. This is the spectrum you see. So what you get here is only the sky, basically. You're zooming, and then zooming, and then zooming, and then you have a tiny little bit of excess here. This is your O2 doublet of your emission line galaxy.
It's the real world.
Okay. And then you subtract it, subtract your model of the sky, and then you fit with the red rock redshift filter. And that's a very good candidate. That's one for which we think we are 90% efficient. So the project is relying on the ability to detect objects at that level. So this is why I think that there are also a lot of instrumental challenges and instrumental systematics that we will have to deal with the Redshift catalogs. So I think you had two talks. I was not able to attend to them, unfortunately, but there were two talks about imaging systematics, one by Arnaud and Ibos, and one by Eli, looking at the target selection for DESI. And I think they have demonstrated that it's already at the level of imaging very difficult to understand the efficiency and the purity, especially for ELGs. And I think we learned a lot from the Ibos experiment on that, but it's actually going to be tricky. But I would like to say that it's also going to be complicated on the spectroscopic side. So, but there is a reality of actually analyzing all this data for DESI. I mean, I see, for instance, in this workshop, all the fantastic work that is being done on the theory and understanding covariance matrices and going to high K and so on. But there are also just reality of processing the data, and this might have an impact on the science that you are thinking about. So, for instance, fiber assignment efficiency. So we have seen that there are some methods for the same target class, for instance, those PIP weights. We can accommodate for that. But the reality will be also that we have several target classes. So you have the imprint of higher priority targets. You have also broken fibers, broken positioners, and so you have to track all of that. Someone has to do the work of tracking all of that. Spectroscopic efficiency, you've seen that it's going to be difficult. It will be a function of the observation conditions. We have more or less sky. Despite the fact that we have automatic adjustment of the exposure time, it's not going to be perfect. It's also going to depend on the location of the focal plane. On the focal plane, we have 10 spectrographs there, and they do not have all the same throughput. It's different fibers. It will be also a function of the target itself. I think this is what Martin was saying yesterday, that we will have a very, the redshift efficiency, your N of Z that you get at the end, will have sharp features because of the skylines. And this will be modulated by the property of the target, how bright the emission lines are for this galaxy. And it will be also modulated on the sky because it depends on the observation conditions. So I don't think that this idea of separating the radial efficiency from the longitudinal, the angular from the radial will really happen. I think it's going to be more complicated than that. And we are going to face that very rapidly. Also redshift precision. A reconstruction in that framework, that we will have some whole, there will be some slices of redshift where you don't know anything. So how do you interpolate over those bands of redshift when you're doing a reconstruction? So that's why I think the work that was sketched yesterday by Mike with end-to-end simulation will be very important for DESY. It's a little bit of tedious work in some sense. It's complicated to take those mocks and to emulate all of the different aspects of the survey. But I'm convinced, and I also agree that doing end-to-end simulations, you have a lot of complexity, and maybe you're not tracking exactly the problem you should be tracking. I mean, it's kind of difficult to adjust the level of complexity in simulations. But it's going to be important. I'm sure those end-to-end simulations are going to be important for DESY. And so this is a message I wanted to say. Okay, so the instrument is totally ready now. It's a fantastic instrument. We have a very good science case. We are in commissioning, so some of us are struggling a little bit those days. But in about 2 months from now, we will start the survey validation. So that's led by Kai and Christophe here, so we can ask them about that. So we are going to validate our target selection. We're going to tune our fiber assignments, how we do it. We're going to validate the spectroscopic pipeline, and also got some help with visual inspections of all of that. And this is going to start, I think, maybe end of March or something like that. I don't know exactly. And then we'll have public release of data every year. So year one, we have to be ready for the science at year one. And I really think we're not ready at all in terms of the clustering analysis. I'm sorry, I think we're not ready at all.
Are we ready in terms of anything else?
I don't know. Okay, thanks.
Yeah, very exciting, very exciting. Many questions. First one is, how do we actually do sky subtraction? You have dedicated fibers, and then you sort of weight medium sky for each of the object fibers?
Yeah, so we have about 40 fibers per petal. So about 1/10 of the fibers are principally allocated for the sky. And then we basically model the sky spectrum, and we are doing forward modeling on those fibers. But we're also tracking the resolution of each fiber separately, and we have, of course, an uniformization of that transmission. And so this very simple approach apparently is working pretty well, but we haven't gone into the second order, which is variability of the sky on the focal plane itself and things like that. So
it's a classic problem.
Yeah.
The other thing is, did you estimate your actual precision on the redshift measurements? How many kilometers per second? Like, I mean, nominally you have 3,000 R3000. So using a single line, you could have something like 100 kilometers per second. But the signal to noise is also very relevant for that, and you show that it is very low. So
yeah, well, so I don't have the numbers in head, but we have conducted simulations all the way, and so for this kind of thing, just statistical precision in the redshift, I think we are. I mean, of course, it's going to be depending on the brightness of the galaxy. We have a good understanding of that, and for all target classes, it's not a limiting factor for the science, except for quasars. And for quasars, I'm not sure we understand exactly yet what we're doing. Like the PDF. In fact, you have large tails for the PDF for quasars, and so there will be a lot of work on that.
but for quasars, we might be better off because we have many emission lines.
Yeah, but they are very broad, and you have a lot. What's complex is the variability from quasar to quasar. It's really depending on the dynamics of what's happening around the AGN. So that's what gives you this shape, this amount of unknown for the redshift of the quasar, and that's actually it's a little bit messy, that part.
It's astrophysical.
It's really astrophysics of the quasars more than measurements and so on.
All right, let's thank Julian again. Right. Next, we have KG, who's going to talk about PFS.
Okay, first of all, thanks to the organizers for inviting me to this meeting. It's always good to be back. So today I'm gonna basically talk about kind of Subaru PFS and what we can do with the cosmic web data that we are anticipating from PFS. So before I even start, I'd like to plug a conference that I'm organizing for the spring. It's basically just an excuse to get plastered under some cherry blossoms. But the deadline is actually today, but I've extended the registration through the end of the week if anyone's interested. But basically, these are kind of relatively generic topic rotating around the cosmic web and large-scale structure. So if you're interested, please sign up. Okay, so the Subaru PFS is a little bit under publicized in the U.S. community. So first of all, I want to talk a little bit about PFS, what it is as an instrument, and also a bit about overview of the kind of the galaxy evolution survey that I'm mostly participating in. And then if there's time, I will talk a little bit about some of the ideas I've been working on in terms of doing constraint realizations of large-scale structure. So first of all, this is the Subaru telescope. It's an 8.2 meter telescope on top of Mauna Kea, which is one of the best sites in the world. FYI, it's not named after the car company. It's named after the Pleiades. So Subaru in Japanese means Pleiades. So both the telescope and the car company are named after Pleiades. And if you look at the Subaru car logo, it's actually Pleiades. So one of the most special things about Subaru is its prime focus field of view. So around 10 years ago, a new wide field corrector was developed for prime focus on Subaru. So this is the prime focus, and it was designed to match with the Hyper Supreme camera, which is the most powerful imaging camera in the world today. So it sits on top of the prime focus. So this is the Hyper Supreme cam with its wide field corrector. This is about 3 meters long and about 3 tons. And and they occasionally switch instruments by lifting the crane over the primary over here. And it's a very terrifying process for a 3-ton object to be floating over your primary mirror. But anyway, so this is currently, before LS60 comes online, it's the most powerful imaging camera in the world. Is a 1.5 square degree field of view on 8 meter telescope. So just to put things in context, this is what the Subaru field of view is compared to other 8 meter class telescopes and also the moon. So you can see that Subaru really stands out by far among this class of telescopes. So about 10 years ago, a new project to exploit the Subaru field of view was developed, which is the prime focus spectrograph. So what it is, it's supposed to exploit the same wide field corrector as Hyper Supreme cam, but instead you're gonna put fiber positioners connected to fiber spectrographs in the adjacent room. So there's going to be 2394 fibers over a 1.125 square degree field of view. And it's optical near IR spectrograph going from about 400 to 1.3 microns. And also it's a facility telescope for Subaru, which means that it's in principle open to the community, and it's also something that has to switch off with other instruments. And And in fact, the UC community would probably have access to a couple of nights of of PFS time per year once it comes online. And once it comes online, it's really going to be the most powerful spectrograph in the world. If you ignore field of view, it's about 4 times more powerful than DESI. So the collaboration has been expanding over the last few years. The PI actually sits next door, Hitoshi Murayama, and the project is being led from IPMU, and the technical work is being done by these institutions: Princeton, Hopkins, Caltech, Asia A, LAM, and AOJ. So that's our survey operations plan. And here's the fun thing: when I show the same video in Japan, nobody laughs because they're like, "What are you laughing about? This is 100% normal." But anyway, so this is kind of the specs of the spectra that we expect to get. So basically, there are 3 channels. The first 2 channels are basically ranging from 400 to about 600 nanometers, and then from 600 to a micron. So these 2 use CCDs, like most spectrographs. And then there's a near IR channel that goes to up to 1.3 micron, and this uses mercury cadmium telluride, mercury cadmium telluride arrays, which are much more difficult to work with. And the characteristic resolutions are about 2,000 to 4,000. There's actually a R5000 mode on this camera as well, which is optimized for galactic archaeology work. So in terms of the construction work, we're a bit behind DESI, but it is progressing. So in fact, about a month ago, the first spectrograph unit was being installed in Subaru. So this is the clean room where the PFS spectrographs are going to sit. And this is one of the, so you can see 4 quadrants here. And this is the first camera being assembled, and you can see the blue and red cameras here. They're a bit bigger than the DESI cameras. But one thing that's a little bit unfortunate is that we have decided to install the first camera without the IR camera because the characterization of the Mercatels are a bit behind. But regardless, this is now at Subaru. The prime focus unit of positioners is being assembled in Taiwan right now, and is expected to be delivered in spring. So the spectroscopic first light that we hope to get is sometime in the summer, where we'll try to get 5 spectra with the blue and red cameras up to 1 micron. And right now the schedule looks like we'll begin science operations in mid to late 2022. So the Subaru telescope does not do GTOs. So even if you build an instrument for them, you're not guaranteed time on that instrument. And instead, we are having to prepare a so-called Subaru strategic program proposal, where we're going to propose for something like 300 to 360 nights over 5 years. And this is kind of the overall theme of the survey, which is supposed to try to connect dark sector and cosmic evolution. There's going to be there are three components to this survey, which is going to be roughly split evenly between these 360 nights. So there's a galactic archaeology survey, which I suspect no one here cares too much about, but basically it's going to be targeting the local group, halo stars in the Milky Way and Andromeda, and most especially going after dwarf satellites and like measuring their velocity dispersions and metallicities, and trying to answer questions like the core cost problem and the missing satellite problem, etc. There is also the PFS cosmology survey, which I'm not going to talk about at all because Tomomi is about to tell you more about it. And then the component I'm most involved in is the galaxy evolution survey, which is basically going to target something like 12 to 15 square degrees and basically hammer on it for 100 nights. So first of all, there's what we call in this context the low Z galaxy sample, which is going to obtain galaxy redshift for a wide variety of galaxies from redshift 0.7 to 1.7. And basically, over this 12 to 15 square degrees, we're going to target something like 250,000 galaxies, which, if you look at the volume and number of galaxies, is actually comparable to Vipers, but at a bit higher redshift. And then the component that's dearest and nearest to my heart is the IgM tomography component, which is going to target IgM absorption from around redshift 2.2 to 2.7 to go after the 3D IgM absorption distribution at cosmic noon. And then going out to redshift 5, there's going to be a sparser galaxy sample that's going after just trying to build up a sample of galaxies selected with near IR imaging, and basically to study the evolution of halo mass and stellar mass relationship, and also gas outflows across this early epoch. And finally, there is an epoch of reionization sample, which is basically selecting Lyman alpha emitters from narrowband hyper supreme cam imaging at redshifts, I think 5.7 to 6.6. So you're gonna constrain the evolution of the equivalent widths of Lyman alpha at these high redshifts, and also we have collaboration with NWA to cross correlate the LAEs with 21 centimeter H1 maps. So for those of you who haven't heard me prattle on before, so my kind of unique science case is the IgM tomography, where I hope everyone knows what the Lyman alpha forest is, where you observe a bright background quasar, you can probe the one-dimensional absorption in front of it. And the idea of IgM tomography is that if you have a configuration of quasars at the back, closely grouped together, you can do a full 3D reconstruction of the absorption in the foreground. So this is an idea that actually that was developed in large part here. And over the past 5 years, we've been conducting the Clamato survey on CAC, which is wrapping up this month. But basically, we've been building up something like 1/6 of a square degree footprint within the Cosmos field to demonstrate this project. So I guess some of you have already seen this many times, but this is kind of the result that we have, which is the blue haze is the absorption that we see in from the Lyman alpha absorption, and the dots are the galaxy surveys that have also targeted the same field. So basically, this is showing that we can study together the galaxies and the gas. And you see that they trace kind of the same underdensities and overdensities, and kind of the differences are where the devil is in the details. So we're starting to study in detail kind of the relationship between the two. But this is about, as I said, about 1/6 of a square degree using KEC. PFS will extend this technique by factor of 50 greater volume. So on to my next half of the talk, which is kind of over the past couple of years, I've been thinking about constraint realizations and density reconstructions. So we've heard about reconstructions in the context of BAO, which is to basically rewind your galaxy velocities to sharpen your BAO peak. In this context, I'm going to talk to you about using reconstructions for slightly more mundane purposes. I'm actually going to talk about two separate approaches. One is by my postdoc Metin, and another is by Ben, who's sitting in the back. And someday two of them are going to have to fight it out, and only one will survive. So the first, which is done with Ben, is this what we've called TARDIS, tomographic absorption, reconstruction, and density inference scheme. So basically, the idea is to exploit the Lyman alpha forest tomography data, which in terms of survey geometry are sets of one-dimensional sightlines probing a continuous absorption field. And so the basic machinery that drives this is this limited memory Broyden Fletcher Goldfarb channel LBFGS methodology solver which drives a fast PM approximate n-body method. So basically the deal is for a given set of data, you basically draw a sample of the initial density fluctuations. You run them through fast PM to get the density field at late times, and then you generate the approximate Lyman alpha forest absorption corresponding to this density field. You do a likelihood comparison, and then you go and then you try to solve for it in this loop. As I say, in this case, the data that you're looking at are a set of one-dimensional absorption skewers that go through this volume. So you can ask Ben. I'm going to skip through all this, but basically, I think to put it in an extremely dumb way that even I can understand is basically just a very clever quasi-Newtonian solver. So we kind of played with validating on a couple of mock data sets. I guess I might not have mentioned it, but kind of the survey parameters we're expecting for PFS is going to be roughly comparable to Clamato. The difference is only in the volume. But the sightline separations are going to be between adjacent sightlines are like a 2.5 megaparsecs, which translates to something like 900 sightlines per square degree. And we've been very aggressive with the signal to noise. And so in this case, we're showing here the true absorption in the volume. And this is actually the spectra that we're going to work with that has this large amount of noise. So these are the kind of noisy spectra are actually what we're going to try to solve for the initial density.
What exposure time on your 8-meter telescopes is that?
On KEC, this translates to something like 3 hours. PFS is slightly smaller and low throughput, so we're probably looking at 10 hours on PFS. So just to illustrate how this kind of algorithm works, so here I'm showing the kind of the initial fluctuations in a simulation volume versus the density field at redshift 2.5, which is dead times in our context. And this is showing the green is the true absorption that we have through one of these sight lines. And then the dashed line is actually the noisy spectra that the solver actually sees. And you can see here, the red is kind of the solution that's being solved for. So you can see here that eventually the best fit absorption does kind of track the true absorption, and in 3 dimensions the kind of phases of the density field seem to come out all right. So just to be clear, there's hundreds of these skewers that's being solved simultaneously in this. So kind of the initial results we had are kind of summarized here, which is that yes, we do kind of by eye get similar phases in terms of the density fields and the velocity fields that we derive at redshift 2.5. But immediately the thing that jumps out is that the amplitudes are off. So so even though the kind of structures that we derive seem to be coming out roughly right, the the kind of amplitude of the fluctuations are underestimated. And basically this is just a limitation of laminar forest, which is that the absorption saturates at relatively low densities. So I think I'm going to skip this, but I think one of the major next steps that we're going to work with is to incorporate absorption and galaxies at the same time. So as I'm going to mention in a little while, typically you also have galaxies, some sample of galaxies in the same sample as your IGM data. So basically combining simultaneously solving for the absorption and the galaxy density field will kind of give you the best of both worlds. So this is kind of a preliminary example where this is a true density field, and this is the reconstruction from galaxies only, where you kind of see that the overdense regions are reconstructed, but there's also a bit of short noise where some of the overdensities are not really well reconstructed. Whereas the Lyman alpha gives you the low density filamentary structures really well, but solving for both simultaneously gives you kind of a very good reconstruction. So I think still work in progress to refine this technique. So the other project that I've been working with my postdoc Metin is to use an alternative algorithm called BERF, which is basically a Bayesian technique to solve for the initial conditions driven by 2LPT and I think some bias prescriptions. So I'm not going to talk much about the technique, but I just wanted to highlight some of the initial results we have. The project we're working on now is to kind of apply this reconstruction technique to Cosmos and high redshift. So basically, as I say, Cosmos is the premier high redshift field. Is roughly a square degree, and it's been targeted by a bunch of galaxy redshift surveys. In terms of co-moving volume, it's about 70 megaparsec over H. And it does probe very well around redshifts 2 to 3. And at these scales, like back in the 80s, people used to talk about pencil beam surveys where you don't expect to get any transverse structure, where you don't expect to get transverse structure. But I think with 70 MPC, you do get some transverse information. So I don't think it's a pencil beam survey. I prefer call it a Sharpie beam survey. But anyway, so the selection functions that we have are, so basically part of the challenge is to try to figure out the selection functions of the various surveys. So this is the angular selection function that we ended up getting from the different surveys. Please ignore this. We've decided to throw this one out because it turns out they don't understand their selection function, so we decided to. But anyway, in these other cases, you can see, for example, the chip gaps in the VMOS CCDs, etc. So the preliminary results is that, as I said, BERF is a Bayesian technique that's driven by Hamiltonian Monte Carlo. So we do get ensembles of posterior realizations of the initial conditions. So just to give you, so this is one realization of the initial conditions, and this is the same realization evolved to the observed density, to the observed redshift, which is from like redshift 1.5 to 3.5. So you can even see the light cone effect where the structures at higher redshift are less pronounced than the lower redshift structures. And then when we stack a bunch of realizations, you'll see where the actual data is, which is within, this is roughly where that square degree is. And we're currently now starting to analyze what we can do with these structures. So one of the cool things about having initial conditions is that you can stick them into a simulation. So this is a preliminary exercise where we plug this into a n-body simulation and let it run. So one of the questions, so the way to see it is that this is showing how the structures will evolve in this field, going from high redshift to redshift 0. And remind you again that these are being observed at redshift 2.5. And the contrast isn't showing up very well here. But there's a couple of well-known high redshift protoclusters that have been observed here. And I think one of the key takeaways from this video is that these two protoclusters here that have been reported in all these multiple papers. Why isn't it finishing? Which is that these structures are likely going to collapse into a single cluster at redshift 0. I'm not sure what's wrong here. It's a very non-linear time progression. But so yeah, so this is kind of the kind of things that we're hoping to do. And as I said, we have thousands of posterior initial conditions. So we think we're gonna have some fun, like looking at the fate of all these structures. So I think I'll just wrap up, and again to say that kind of the stuff that I've been showing for Cosmos and Clamato is going to be really kicked open by PFS by factors of 10 to 50. And yeah, so I'll finish and take questions.
We have time for one question. Jeremy.
Too short.
That's acceptable.
So I read in earlier descriptions of PFS that the galaxy evolution survey is subsample. Is that still the case? And if so, what is the subsample rate?
I think it's 80%. It's.
What is the point of that?
In which direction?
Why not just do overall?
I think it might be. I think part of it is just fiber collisions that, especially with clusters, like it's hard to within a finite amount within the.
So it's not a subsample rate; it's just what you actually can expect for after.
Yeah, and I think it's. I need to check the numbers, but I'm pretty sure it's around 80%, and part of it is just things that we can't get to. I think I can look up the numbers for you and talk offline. Yeah. The public data release. I think it will follow the. There will be public data releases, and I think the best analogy would be to see how Hyper Supreme Cam did their public data releases. So I don't think there's like strict plans, but there will be public data releases. And I think as a meta indicator of how that's going to progress, you can look at the, I would say about, do you know, I'm actually not sure. I would say within 2 years of any data tag would be, but yeah, we will make it public at some point. It's not private for 99 years.
All right, let's thank KG again.
So I will mostly talk about PFS like cosmology, since PFS has 3 science components and I'm working mostly for cosmology. And first half is like general science goal for PFS. And the latter half, I will talk about fiber assignment artifact on clustering. So this is a list of the science goal for different science working groups. And the blue lines are the things that cosmology working groups are planning to do. So constraining dark energy and testing theory of gravity using BAO and redshift space distortions, and also constraining the sum of neutrino mass. And cosmology survey will cover 1400 square degree with 4 million emission line galaxy spectra. And this is a figure of the number density of galaxy times the power spectra at k equal 0.2. And because PFS uses Subaru 8-meter telescope, we can actually reach very high number density. And also we can go to like high redshift up to 2.4. And this is the area that we will cover, which is the same as HSC. And for cosmology, we will use a wide area, which also overlap with ACT and also Sloan. And we have a blue, red, and IR component. And this IR component makes it possible to measure the emission line galaxy from 1.6 to 2.4. And the tile that we will use is a hexadecapole. And we will uniformly place the tile and visit the same area twice. And we are planning to do to spend 15 minutes for each exposure time. And the fiber density for PFS cosmology is 2200 square degree. And the left figure shows the constraining power of PFS and DESI as a function of redshift. And for BAO measurement, area matters much more than the number density. DESI will do better than PFS, but the unique component of PFS is that we can constrain, we can measure BAO from 1.6 to 2.4 using emission line galaxy. And the right panel shows the growth of structure as a function of redshift. So one science which is complement with DESI is that a mild tension between Lyman alpha BAO and galaxy BAO, where the contour don't really overlap at the center. And since DESI will measure, we'll do Lyman alpha BAO for higher redshift, this can be complement with PFS emission line galaxies. Also, by using the HSC weak lensing and PFS clustering for redshift space distortions, we can test the gravity by cross-correlating PFS and HSC or PFS and ACT pole. And the constraining power for by using HSC and ACT pole are almost comparable, although like at higher redshift, the constraining power of ACT pole is stronger. So now I will more focus on the PFS tiling and fiber assignment and how it actually affects to the galaxy clustering. So the difference between Sloan and PFS is, one of the things is that Sloan or both have very high success rate, and the number of target is actually much smaller than the number of fiber. On the other hand, for PFS, the number of target is larger than the number of fiber, so we have a lower success rate, which means that when we miss true galaxies from the target list, that actually affect much more on clustering. And also the redshift range that PFS will cover is much deeper, which means that when I compute the angular clustering from the target galaxies, because of the deep redshift coverage, the clustering will be almost uniform, which means that for fiber collisions, sometimes people use angular clustering to correct for the clustering, but that method is not applicable for PFS. And the other thing is that for Swan, the major problem which affect to clustering was fiber collisions. But for PFS, the nature of the problem is similar, but because we use finite patrol, we use robotic fibers, and because each fiber has finite patrol area, that actually affects more. So when I run the fiber assignment code to the galaxies, this is the clustering that I get. So the black line is a true correlation function, and the blue line is after I run the fiber assignment code. So as you can see that the amplitude is suppressed on all scales. And the right panel shows the ratio between the correlation function between post fiber assignment and true samples. And blue line shows the angle averaged ratio, and light blue and orange, I show like transverse direction and line of sight direction. And what this figure shows is that line of sight component is much more affected by the fiber assignment. And this clustering, this correlation function is computed in real space. So any like angle dependent feature shown here is purely caused by the fiber assignment. So for this program, there are two codes, and one is tiling. Because PFS have much higher number of target galaxies than the number of fibers, when we use a fixed number of fibers, that actually eliminate the long wave mode density fluctuations. And the other is the fiber assignment by robotic fibers, which preferentially select galaxies in underdense region. So the figure shows the likely probability to be observed for each galaxies, and the galaxies which have high probability are the ones which are in underdense regions. So in order to fix the first problem, what we do is weighting method using the number of fiber and number of target to recover the long wave mode density fluctuations. And this actually recovers the correlation function on large scales. But the number of target that we know is not exact. There will be some photometry error. So the question is, what is the required precision for photometry error for the number of target galaxies in order to use this method? So I assign the Gaussian error for each number of target, and different color shows the size of the error. And what this figure shows is that if photometry error is roughly 1%, that won't cause any problems. But if the photometry error is larger, this method doesn't work. So Shun Saito at Missouri estimate what the photometry error for PFS and DESI. And for both PFS and DESI, the photometry error is less than 1%. So this method is usable. Although for the MGLS and BUS, the density fluctuation, target density fluctuation is 1.1%. So it's very close to the limit. But this method doesn't solve all the problems. On small scales, you still see the suppression of the clustering. And if I check the correlation function in transverse direction and line of sight directions, this method actually overcorrect for the transverse direction component, and which compensate with the line of sight suppression. So this method is not fixing all the problems. So the survey design for PFS, and this is a schematic picture of the patrol region for each fibers. And the way we decide to visit the same area twice is to maximize the fiber allocation efficiency. So for PFS cosmology, the mean number of target for each fiber is 3.3. And with this number, when we visit the same area twice, the fiber allocation efficiency is 90%. So there won't be many wasted fibers in the observations. So in order to simplify like how this patrol area affects to the clustering, I simplify the program. This thick line shows the tile, and the grid shows each patrol region for fibers. But in this way, patrol area doesn't have any overlap regions, as well as any algorithm which has to take care of like what target to be observed when they are very close. So in this way, if there are 3 targets in grid, I would just select 2 of them randomly. So the probability to be observed is 2/3 exact. And if I use this probability as an inverse weight, this actually fixes the clustering on small scales. So this is the same method as Bianchi, who talked about this method yesterday, but the problem is simpler. And this shows like how the clustering is actually, how the number of visits matters for the clustering. And because the nature of the program is that when we have very small number of visits, the line of sight clustering is severely affected. And so the left panel shows for the transverse direction, the number of visits doesn't really change the amplitude, but by increasing the number of visits for the line of sight direction component is getting improved. So by using this IIP, the question is that whether this method works for the actual fiber assignment code. And so I run the same fiber assignment code 100 times to obtain the probability distribution and use this probability as inverse weight. And this actually recovers the clustering at a scale greater than 10 megaparsec with the accuracy of 1%. So this method works. So as a summary, PFS is one of the key strategic instruments of Subaru, and PFS cosmology can reach to test the sum of neutrino at 0.1 eV threshold, and also measure the clustering at redshift greater than 2 with emission line galaxies, which can be complemented with DESI and Euclid. And also fiber assignment problem can be solved by weighting method. Although like currently, like we only test this method on 2-point correlation functions, and it's not clear whether this method works for bispectrum or void statistics. And so for the current status of the target selection, with the new Cosmos mock catalog and using a simple color cut in G-R and G, the expected number density at higher redshift is actually smaller than like originally expected from Takada 2014 paper. So if you know like any better way to do the target selection for high redshift galaxies, I'd like to know your opinions. And also, we are still looking for some international partners. So if you're interested in joining PFS, please talk to either Hitoshi or Masahiro. Thank you.
Any questions?
Just one, the last slide you show that your color selection at the moment is just color magnitude selection.
Mm-hmm.
I think you have photometry also for a redder band like I or Z, right?
Mm-hmm. Yeah.
So did you experiment with the G minus R versus R minus I, for example, or R minus Z? Normally that provides you a better cut. I mean, if you want to cut off low ratio galaxies, like with Vipers, for example, we had a very efficient cut to low ratio 0.5. Basically, 2% the contamination and 3% completeness. The high ratio is
I see.
allowed us to double the number of targets in the distant part of the sample. So I don't know if you have tried also already.
We are not testing yet. So yes, thank you. Yeah.
Any other questions for? I have a question.
Yeah.
You put up in the summary slide that PFS forecasts 0.1 EV constraints for neutrinos. How does that compare to what Julian just showed us of 0.02 EV?
I think for neutrino, we are actually comparable. Yeah, because for neutrino, small scale clustering helps to increase the constraining power, and we have higher number density.
So I guess my question, I should have phrased this differently, is why do you think there's such a big difference in the forecast that you yours and Desi's?
Sorry. So I think this depends on like what model you assume and how to constrain. So if we assume rounded CDM, we can do better than 0.1.
Okay.
Yeah.
Well, if there aren't any other questions, let's thank them when we get. Okay. Next, we have Yun Wang talking about future galaxy redshift surveys with Euclid, LV First, and beyond.
First, I want to thank the organizers for inviting me to come here and tell you about the space missions that I've been obsessing over for many years now. So Euclid, W First, and beyond, but here beyond is actually limited to the 2 space missions that I'm the PI of. All right, so first Euclid, W First, then my probe mission concept called Atlas. So since I'm standing between you and lunch, I will try to keep this high level and light and enjoyable and hopefully inspiring. So Euclid, so where did that come from? Well, so ESA had a cosmic vision call for medium class missions, and there were 2 winners, Space, that Gigi and I were key members of, and Dune. So it's spectroscopic survey mission and the imaging mission. Of course, the ESA way of doing things, right, is to combine this, and now we have Euclid. So it's the great news is that Euclid has been very successful, and we're on track to launch in 2022. And so this shows the engineering model for Euclid. So it's, right, we're almost there. And
actually, most of that will fly. So what you see there will fly. So just a few pieces which are not on. I checked
right, the
this.
flight model will have, the flight
Yeah.
model
Flight
will
is
have
basically
some
made of pieces of
differences.
that,
Yeah, but this is there for the engineering test. Yes, has. So Euclid passed the mission critical design review November of 2018, right? So if we want to use NASA speak, phase C actually ended over a year ago. Now we are in phase D. It's the final phase before launch and operations. Okay, very exciting. Euclid is happening. And Euclid will carry out a 15,000 square degree survey of both imaging and spectroscopy. Okay, so it's actually at, right, so this is the galaxy at high, well, cleaner parts of the sky, right? So it's at up here and down here. And the little patches are the locations of the Euclid deep field for calibration. And so the Euclid, for the purposes of this meeting, what you want to know is the galaxy redshift survey. We should get at least 20 million HR5 emitting galaxies at a flux limit of 2 × 10⁻16 ergs per second per centimeter square. And so that's redshift 0.9 to 1.8. So what's important for those of you who are theorists to keep in mind is that sometimes it's very confusing and misleading to compare redshift ranges. The only unique number is wavelength coverage, okay? So here for space missions, we focus on what you cannot see, at least not easily from the ground. So the Euclid spectroscopic coverage from space is 1.25 to 1.85 microns. So we just heard the talk on PFS, right? So there, it ends at 1.3. I think DESI cuts off perhaps also around that there, perhaps even bluer. And so, of course, the downside of Euclid, right, by being so ambitious, going so wide, and we do have some risk. I'll come back to that later. And also putting a plug for my postdoc, Zhongxu Zai's poster on the number count forecast. And I know some of you are members of the Euclid Consortium. And so I like to put this in case you're a US member who is not yet plugged in to the Euclid work package structure. And so there are 2 primary science working groups within Euclid Consortium, one on wake lensing, one on galaxy clustering. And so I'm the co-lead for the galaxy clustering with Gigi and Will Percival. And we have these different work packages. This is our second round of work packages, right? So we evolve these as it becomes clear what's needed. And now, perhaps this would be of interest, at least to some of you. Right, so I will not read what's here, but basically NASA is making significant hardware contribution, I should say critical hardware contribution to Euclid by providing the near-infrared detectors, right? Also NASA selected 3 science teams to join Euclid several years ago, okay? So also NASA is funding US participation in Euclid ground segment. So in the entity called ENSI, Euclid NASA Science Center at IPAC, that's where I work. That's why I moved to Caltech, actually. They recruited me. And so now, what this means is that we have infrastructure to support US scientists who would like to work with Euclid data. And so if you have questions about Euclid, you can actually go to our website, inside website, and submit a ticket. Okay, so you know that if you don't know how to get involved on Euclid and what to expect, just submit a ticket. So Euclid will have public data releases. So this is from 2013, but there's no update since then. Okay, so this is a notional plan for releasing Euclid data. So I should say that this is actually more generous than a typical public data release of the ESA mission. Okay, so there was, I remember some years ago, there were a lot of debate about that. I'm sure Gigi remembers as well. And so the Euclid scientists who were in favor of sitting on the data for 5 years before releasing it lost, I'm happy to say. Now, moving on to WFIRST, further into the future. So Tim Eifler already gave us, he showed this same image actually, the background for WFIRST, right? So that came from a long path, right? So some of you remember Jaden, right? I was PI Jedi, some of you were on Snap, right? So Jaden, unfortunately that went nowhere. But then we had this beautiful, amazing 2.4 meter from that agency we're not supposed to name. So then I think that all of a sudden made WFIRST very exciting and spectacular, because it's like having HST, right? Except with 100 times bigger field of view. And also, I've been on all the WFIRST committees, various. During one of those committees, we successfully argued to upgrade the detectors from H2RG that everyone uses to H4RG, right? So WFIRST will be the most spectacular near-infrared imaging instrument out there from space, so you can, actually take full advantage of that. Well, so most of us are based in the US, and the decadal surveys set the priorities for both NASA and ground-based astronomy in the US. And so WFIRST was the top priority from the last decadal survey. So NASA follows the recommendation of the decadal survey to the letter, I can say that. So that's why WFIRST is going forward. Here's a timeline. And I won't bore you with all these details that you may or may not be interested in. So I want to point out a few things. So now in 2015, NASA selected in an open competition a number of science investigation teams, which in total include over 200 scientists. So I'm on one of those teams. I'll show you a slide showing my team. And then phase A started in 2016. That's when NASA adopted the mission, okay? And then phase B started in April 2018, okay? And we are about to start phase C. And so now, WFIRST, as Tim pointed out, has had some interesting bumps, right, because of politics. We were supposed to be canceled for, each year briefly, right? So anyway, but it's actually on track. It's fully funded for fiscal year 2020. So it's on track for launch in 2025 for 5-year prime mission, but the goal is 10 years. The the science team that I'm on is led by Olivier Doré and Chris Horetta, that you guys are all very familiar with. Is the weak-lens need, and I'm the Galaxy Redshift survey need. And so we have a website. So I want to point out something that should be of great interest, perhaps to everyone here, right? So NASA selected, as said, a bunch of science investigation teams in 2015. And NASA will disband all these teams, including mine, the one I'm on, sometime next year, because NASA wants to have another round of open competition for the next round of science teams. Those will be called implementation science teams. So the ones we have now are called formulation science teams. It's complicated, but it's great, right? So they will give the community more opportunity to participate in WFIRST. I think Paul Hertz, in his recent overview at AAS, put in big letters saying WFIRST is your mission. You means the US community, right? So nothing is fixed, okay? And including the scientists who are on one of the current teams, right? So we will be disbanded and then we will all, compete again, fresh. And so having said that, I can tell you that we do have reference missions, right? We have notional surveys to help define the mission. But then what will be done will be determined by the next round of science teams to be selected by NASA in an open competition. Okay, that will actually be what will be implemented on WFIRST. Okay, so what we have now are reference surveys, which may or may not happen. Okay, so in this notional plan, 1.5 years is allocated for weak-lens and imaging. Only 6 months is allocated for galaxy redshift survey, and 6 months for supernovae. Okay, so of course, planets mostly, through microlensing gets 1 year. There's also the chronograph, mostly for tech demo. Also very important, at least 25% of the time during the prime mission will be devoted to guest observers. Oh, last point, which hope you can see. So very important decision was made in the last committee, is to make all WFIRST data available immediately without any proprietary period, which is unheard of, right? So of course, I can tell you there were a lot of hand wringing, a lot of angry shouts about, oh, you're gonna push us to flood the field with garbage data, but then NASA said, well, we will select teams who will produce quality data, which will be made available to the community immediately. So we'll see. Okay, so I think that NASA, all these decisions that NASA has made, for example, having 2 rounds of competition for the science teams and having 0 proprietary time, is to drive home the message that WFIRST is a mission for everyone in the US. Well, we also have international participation, that's other. So this is one of the first batch of simulated WFIRST images. So this, everyone can see, is Andromeda. So this is just to compare the WFIRST field of view, say the 18 detectors, right? And there's the moon, and this faint blue contour is the biggest HST survey and that was led by Ben Williams. Okay, so I think Tim showed this as well, right? So this painful, huge HST program can be done by WFIRST in 2 pointings in half an hour. instead of 650 hours on HST. Okay, that shows you the power of Doppler first. Will be extremely capable. We don't really need to look at the exact details just to show you that. So here's the instrument, right? So we're interested in the wide field instrument here, and that's maybe this is more interesting to people who are technically minded, right? So the one that's of most interest for this meeting is the Galaxy Redshift survey that uses PRISM, okay? And so these, minimum, maximum wavelength are not written in stone either. The only constraint is that the maximum wavelength can't exceed 2 times the minimum. I've actually been pushing for just making that 1 to 2 microns, but this is one version, right? So when they design it and fine tune stuff, and also the guest observer science teams have different preferences, right? So but it's a pretty wide coverage. And the requirement that I've set for this is so that the W1st Galaxy Redshift survey will be able to use at least 2 emission lines in measuring redshift, right? So that will get rid of some of the systematics.
Sorry.
Yeah, go back.
The resolution is 461 lambda in 1 unit.
Lambda is in microns.
Okay.
Yeah, so the meaningful number here is actually spectral dispersion of 10.85 angstroms per pixel. you convert that into this, right? So it's a wavelength dependent, but it's a prism, so it's what's fixed is actually the spectral dispersion. In reference for Euclid, it's 13.6, right, angstroms per pixel. So it's higher spectral resolution than Euclid. Tim showed this figure as well. This is a notional coverage of the high latitude survey, that's 2,000 square degrees on W1st. And so that's always confusing to look at. So why is it called high latitude, right? So here's in galactic coordinates, so you see it's high latitude. Why high latitude? Because when you go to space, you don't have to worry about atmosphere, but you do have a zodiacal background, right? And so the zodiacal background is lowest as you go to higher latitudes. So we'll have the notional plan calls for 2,000 square degrees in both imaging and spectroscopy. And we expect to have approximately 10 million HRFI emitting galaxies at a much fainter line flux, 10 to minus 16 ergs per second per centimeter squared, and at much higher significance compared to Euclid. Okay, so again, I like to round off the redshift range to 1 to 2, right? And also round off the wavelength range, partially because none of those are written in stone. It's just, ridiculous to add the decimal point there. Since W1st expects to go much deeper than Euclid, we should also have a significant enough number of O3 emitting galaxies that we can probe dark energy with from redshift 223. So here I put down 0.6, meaning that's based on this flux limit. Well, if we go to 5 sigma, we can go deeper. And this will actually increase by more than a factor of 2. And again, I point you to Zhongxu's poster that's still out on the 3rd floor for the number count predictions. And again, very important here, right? So I'm very happy that I've insisted on measuring redshifts only using spectra with at least 2 emission lines. So I think someone mentioned yesterday that W1st only use 1 emission line. That's not true. We use the higher signal to noise line, HRFI, to get the actual number or to require the presence of a second line. So this is a useful slide from David Weinberg. Oh, that's Neil Garris, who was the project scientist for WFIRST, and he passed away because of cancer, and so he's been missed, obviously, right? So, so here's David's nice summary of why WFIRST is exciting, and so the ultimate supernova cosmology experiment. I think we can say that because it's at 2.4 meter, right? So it's much easier for us to use this to observe supernovae than say Euclid 1.2 meter. And also we have, yeah, so just leave it. And also the best controlled wavelengths in experiment. Again, because it's a much bigger mirror, right? So we can afford to have multiple bands in the near infrared, right? So that the shape measurements will be much more accurate, and we can control the systematics better because the pixels are just much smaller than Euclid. And so for galaxy redshift survey, so he put down Benz's large-scale map of structure, and I will actually back that up with some numbers. Oh, wow, time flies. Okay, let's move forward. Okay, so, right, so it's nothing's written in stone, and so WFIRST will be powerful for galaxy evolution. So now let's move forward. So this compares Euclid and WFIRST. I think I've said many of these things already. And so there are problems with slitted spectroscopy. And so then, of course, if we talk about going beyond Euclid and WFIRST in space, we should go to slit spectroscopy. So this beautiful figure from Gigi, right, shows you that if you what you really want in your dream, right, is to have SDSS main survey at much higher redshift going all the way, right? So Vipers give you a flavor of what that's like. And so KG's surveys on PFS will extend that. But what goes here is Atlas probe. And I don't have time to dwell on that, can come back to that later. So this is my probe concept that will give us the ultimate 3D map of the universe, going all the way to redshift 7 and beyond. And so you may be disappointed to hear, or maybe you're happy to hear, the science driver for Atlas probe is not cosmology or dark energy, it's galaxy evolution. Well, of course, you would not be surprised to hear it's also the ultimate cosmology mission. Not a coincidence, of course, right? So to have an exciting space mission, you want it to be as broad as possible. So about galaxy evolution, so here's a comparison, right? If you have a photometric survey and you can't claim to see the cosmic web, right? With Euclid or WFIRST, you have a slitless survey, so you get a somewhat fuzzy picture. With something like Atlas, right? All of a sudden, everything snaps into focus. You are indeed probing the cosmic web and being able to understand the physics of galaxy evolution. And we'll have a 3-tiered strategy to probe the physics of galaxy evolution. And so cosmology, so I know, right, a lot of us have our own forecast code. So here, I run all these using my own code. And so the DESI numbers are from the DESI science book. The point here, right, is not who is better or whatever. So here, I just want to make a single point that with something like Atlas White survey, you have extremely high galaxy number density, you really gain, okay, you kill on 3-point statistics. So Lado Samusha, did the voluntarily did this forecast for us. Well, I had community workshop, he came in order to give a talk, he got the number densities and he did this forecast. It was amazing. Okay, so it just came out of nowhere and extremely helpful. Okay, and of course, to make that happen, right, a lot of work will need to be done. Of course, Atlas Pro will, in fact, deliver breakthrough science in nearly all areas of astrophysics. So for example, for the Milky Way science, we can actually penetrate through the center, the dusty center of the galaxy. And running out of time, right? And we can even have a pretty ambitious survey of the Kuiper belt objects, which some people find very exciting, but probably no one here. So what's the enabling technology? It's the same as used in the overhead projector here. Okay, it's called the digital micro mirrors, digital micro mirror devices, or DMDs. Oh, by the way, that's a single human hair. Okay, so Atlas will use this 2K by 1K array of DMDs. Each little micro mirror acts like an effective slit, okay? And these can be programmed to tilt one way to select a galaxy for spectroscopy, or the other way, to bump the light into an imager or light dump. And so it has been used for multi-objects, has been used for spectroscopy from the ground for well over a decade now, right? So the next step is to fly these. And that's why I have proposed a pathfinder for Atlas called ISKIA, Inferred Small Set for Cluster Evolution in Astrophysics. And we were selected for mission concept study by NASA in September 2018, which was very successful. And building on that, we submitted a mission proposal to NASA in August of last year. So now it's under consideration by NASA. Well, wish me luck, right? So it would be really exciting. So why do we need this? Because for Atlas, we will have like 4 identical spectrographs, each use a DMD, right? So the showstopper for DMD in space astronomy so far is that no one has successfully been able to fly one, right? So ISKIA will fly one, so it's kind of like a miniature Atlas, right? We'll map the cosmic web for 20 clusters at cosmic noon. Some people find that very exciting. And right, so it's a small satellite. It's a category that NASA astrophysics is just beginning to look into. I think in other branches of NASA, they have had that class of mission. So it's tiny, right? So the life cycle cost is capped at 35 million, plus 10 million free launch by NASA, because NASA really wants to see what you can do. I think the NASA's slogan for small sets is, pushing the envelope on big science from a small set. So we'll see. So ISKIA is like the poster child of big science from a small set. So be in low Earth orbit. And we have a survey strategy where we will go extremely deep within each cluster and go shallower around each cluster to map out the cosmic web. And so the mechanical model, and my industry partner putting an amazing amount of work. So it's all we have all the numbers, so we can start building it, next month if we get selected. Of course, first will be phase A. And so this is a close-up. So that's a DMD, right? If you look closely, it's one mirror. And so Andrea Andrea Weiss on my team has done simulations of how you select galaxy targets using DMDs. I can tell you it's a lot less painful than fibers, right? Just the fact that you can show anything you want right on the screen using DMD, that gives you some idea of how easy it is to program these things, right? So for example, here is a 10 by 10 close-up, right? We only use one DMD, one micromirror in one row of micromirrors, and we leave one row unused. That means I have 2 rows of pixels that's unused, right? That guarantees 0 overlap and very dark, high contrast spectrum. And we can also have slots to measure the sky. And so for the kind of DMD Atlas needs is a TRO 5-ish, right? So because the TRO 6 DMD is actually slightly smaller. So it's the space quantification work was done by someone on my team, someone who's on both of my Atlas and Ischia teams. So Minkoff, he used the smaller one because they're much cheaper. The bigger ones are called Cinema 2K, as you can tell, right? They used to be used in cinemas, so they're more expensive. But they are actually identical in architecture. So for Ischia, the 0 risk, we go with the TRO6 DMD. But for Atlas, we'll need to do some additional vibrational tests because it's slightly bigger, right? But no surprises expected there. So I will leave you with this. Just want to point out that the most useful way to compare different surveys is not redshift. Okay, it's wavelength. Look, do from focus on space what you cannot do, at least easily from space, from the ground. Okay, so so for Euclid and W first, as you see, we are already exploring a big range of wavelength not easily accessible from the ground. And for Atlas, we go to 4 microns. Just think of what you can do, what you will see. And so here, yeah, so the future, I think, is just spectacular, right? For cosmological galaxy redshift surveys from both space and ground, right? I'm very excited that DESI is already underway. And PFS will come online soon. And so everything we do in space, again, is complementary to what we do from the ground. And so now, one thing that's useful for theorists out there is that for Euclid, right, we expect around 1,300 galaxies per square degree. For W first, that goes up to 5,000 or higher. Okay, for Atlas, look, it's almost 10,000. Okay, it's pretty amazing. And the other thing is that by design, we're decreasing the observational systematics. Okay, so Euclid has, split the spectra with single emission line mostly, but we'll launch first, right? And then for W first, we will have at least 2 emission lines. Okay, and then for Atlas, we'll have all of the emission lines from 1 to 4 microns. Okay, so it's the dream of the galaxy evolution people come true. And it's also spectacular for doing nearly no observational systematic cosmology. And the other thing is that then we can talk about multiple tracers over the same redshift range, right, with something like Atlas. Thank you.
We have time for one very quick question, if anyone in the audience has.